So I'm going to talk about Bose-Einstein condensation of exciton polaritons. I come from Australian National University and am associated with the new Australian Centre of Excellence for Future Low Energy Electronics Technologies. There's a few people in the audience today from this centre. This is the first time I'm using this presentation template because the centre is about to kick off. Very exciting. Okay, so because this is going to be the one and only talk on this subject, I'm afraid I have to give you a very brief introduction to exciton polariton physics. Then I'm going to talk a little bit about the fun we had with so-called fragmented condensation in optically induced traps, and in particular exploring non-Hermitian quantum physics with optically trapped exciton polaritons. And finally, I hope to talk about our recent work on polariton condensation in a single shot regime, where we drive the system beyond statistical averaging. So our group at the ANU combines experiment and theory. Today I'm going to talk more about experiment and theory, but we do both. So this group was established back in 2013 and still remains quite unique in Australia. There is a lot of exciton polariton research here in Europe and in the US, as many of you probably know, but in Australia this is not so. We're quite isolated, but if you're interested in our research at large, there is a web page which can give you some insight into what we do. So let me start from the promised introduction. You probably heard quite a few talks during your recent lifetime on exciton polaritons, and you heard it said that polariton is a half light, half matter composite boson, which is almost completely true. So exciton polariton is a hybrid state which is formed by exciton and photon in a strong light-matter interaction regime, and this regime is usually reached when both exciton and photon are strongly confined. So a typical way to confine a photon is to do it in a semiconductor microcavity between high reflectivity mirrors, for example, distributed Bragg reflectors. We normally work with gallium arsenide L-gas microcavities that reach Q factors of 10 to the 6. That's roughly the number of round trips for a photon in a microcavity. And the excitons are hosted in a quantum well, so in a two-dimensional environment, which are grown to coincide with the antinodes of the photon field, so that the two cannot escape from one another. Once the strong interaction regime is reached, we have an anti-crossing of the bare cavity and exciton resonances and produce two new branches, the upper and lower polariton, which can be tuned by tuning the detuning between the exciton and cavity photon. So if we look at the dispersion, which is the energy versus momentum in the plane of a quantum well, then our bare cavity photon and the exciton, which has a hugely dissimilar effective mass, so it appears flat here, no longer exist. Instead, we have this upper and lower polariton, and it is actually this pronounced minimum in the energy of a lower polariton branch that gives rise to the possibility to reach a quantum degenerate state of these bosons, to condense them all into this energy minimum. So about this half-light, half-matter business, this is not quite true. In fact, it can be tuned to be anywhere between light and matter. A polariton can be made completely photon-like or exciton-like by changing this detuning between the exciton and photon resonance. Usually it's achieved by having a wedge, a length wedge in the microcavity during the nanofabrication process. So we actually tune not the exciton resonance, but the photon resonance. And the effective mass of the lower polariton is proportional to the effective mass of the cavity photon divided by the square of the Hopfield coefficient. and ends up to be quite small. So it's about 10 to the minus 4 of the exciton effective mass, or free electron for that reason. So exciton polariton as a mixed light matter particle inherits a few nice properties from both photons and exciton. From photon, it inherits fast propagation speeds of micrometer per picoseconds and quite short lifetime. The jury is still out whether it's a good thing or a bad thing. And from the exciton, it inherits the strong interactions, relatively strong interactions due to the Coulomb repulsion. There's also a mixed property, which comes from both photon and exciton, and it's spin, but I won't be talking about it today. Okay, so the spontaneous condensation of exciton polaritons is a driven dissipative process. So it's a truly non-equilibrium process. What is usually involved is an off-resonance CW pump that injects hot, high-energy free carriers into the system. Then they relax down to the lower polariton branch by a combination of radiative and non-radiative processes. By latter, mean relaxation by interaction with lattice phonons, for example. And then they accumulate in this bottleneck region, which forms largely excitonic reservoir of quasi-particles. So this bottleneck is a relaxation bottleneck and appears due to the large jump in the effective mass in this region. And from there, transition to the ground state is only possible through stimulated scattering into the ground state from this thermal excitonic reservoir. So stimulated scattering means stimulate bosonic scattering. So the density of this state needs to reach a certain threshold from which the process kicks in. And it is due to the polariton-polariton interactions. Now, once the condensate is formed in the ground momentum and energy state, it continuously escapes, releasing coherent photons from the microcavity, and this photoluminescence signal carries all the information we need about the condensate. So momentum, energy distribution, probability density distribution, correlations, everything. This is an iconic picture from the Nature paper in 2006 when this condensate was first obtained. You can see the photoluminescence images that show the real space and momentum space condensation transition, and I think they sort of intentionally made it look like the iconic picture of Bose-Einstein condensation in ultra-cold atoms. Very similar phenomenon. Now, what is actually so exciting about exciton polaritons? Pun is not intended. There are other massive bosons that condense, so atoms and excitons. But when it comes to polaritons, it has the smallest effective mass of all of them. And that means that the condensation, critical temperature for condensation, can reach room temperatures in certain semiconductors. So that's very attractive. Now we have all this physics of Bose-Einstein condensation, superfluidity on a semiconductor platform at room temperatures. So in principle, very attractive for optoelectronic applications, can integrate it into microchips. Also, in terms of non-equilibrium dynamics, thermalization time relative to lifetime is not very large at all. So it is actually a highly non-equilibrium system, which at some points we can argue doesn't even thermalize. All right, so onwards to the first sort of topic, which is optically induced trapping for exciton polaritons. It is not necessary to trap exciton polaritons to achieve condensation. But if we do trap them, condensation happens faster, and we can manipulate the condensates in a very nice manner. So the idea behind this optically induced trapping potentials is very simple. The off-resonant optical pump does two things. at the same time. It creates polariton condensates and induces trapping potentials for polaritons by introducing local blue shifts in energy, which are proportional to the density of the injected reservoir excitons. So, and these blue shifts are actually exciton-polariton repulsion interactions. So these are repulsive barriers due to the exciton reservoir introduced by the pump. This nice picture, which I borrowed from a paper from Southampton group, demonstrates the effect schematically when we pump the microcavity with the LG laser beam. You can see the condensate forms nicely in the middle of this effective optical trap, and the mode distribution of a ground state is very nice and smooth. This is not always what happens. More often than not, the condensation in optically induced trap is fragmented, which means that the condensate simultaneously occupies several single particle energy states in the effective trapping potential. The examples are presented here. This one is an example of single particle energy states formed in the trap, which is composed of this optically induced repulsive barrier and actual physical barrier. This is the end of a microrod, so it's a hard wall. So you can see the energy levels here. And this nice example is basically a visualization of the equidistant energy levels of the one-dimensional harmonic oscillator, quantum harmonic oscillator, which is formed between two tightly focused pump spots in the microcavity. So this is a typical picture of condensation in the optically induced trap. As far as modeling goes, most of these effects are surprisingly well described by a very simple mean field model. For those who work with ultra-cold atomic condensates, Bose-Einstein condensates, that's probably not so surprising. But nevertheless, the model that describes these effects is called open dissipative Groth-Spitayevsky equation. It was first introduced back in 1998 as a model for ultra-cold bosonic condensation of atoms, in particular for continuously replenished atom laser. And then it was adapted in 2007 for the condensate of exciton polaritons. So what it has is essentially Groth-Spitayevsky equation for mean field, for the wave function of the condensate. In the absence of the external potential, it has condensate and reservoir interaction terms. It is amended by stimulated gain terms and condensate loss, and of course coupled to the rate equation by which all effects of the reservoir are described. So this is essentially equation that describes the stimulated scattering from the reservoir into the condensate mode, the decay of the reservoir, and of course the pump that replenishes the reservoir. So very simple model and works surprisingly well. What is essential, however, is that the effective potential in which the condensate sits is produced by the reservoir, and also that this effective potential is essentially non-Hermitian.
Yes. You mentioned that there is a fragmentation in the condensate of several levels occupied. So how do you incorporate it to Groth-Spitayevsky?
Yeah, so this equation essentially only describes a single steady state in a system. So in order to incorporate many levels, we actually need to amend this, to extend this model.
And in this fragmented condensate, is it supposed to be a cat state, where there's an entanglement between them, or it's all a product state?
So you can think about it as basically several macroscopically occupied states which have Rabi oscillations between them. So in principle, you can write a mean field equation for each of these states. Okay, so what is important to realize is that in this mean field model, the potential that is felt by exciton polaritons is inherently complex. It has both real and imaginary part. The real part is due to exciton polariton interactions, a blue shift, which is essentially proportional to the reservoir density. And the imaginary part is due to gain provided by the pump and polariton decay. And the neat part about it is that both parts of the potential can be manipulated simultaneously and independently. What I mean is basically presented in this schematic diagram. Say we have a pump, doesn't matter what the shape is, let it be a square, and then we have a condensate mode, a single mode sitting in this pump defined potential. So essentially, the energy, which is a real part of the complex eigenenergy, will be defined by the inner area of this shape and the height of the potential wall. But then the imaginary part, which is the line width of the complex eigenenergy, will be defined by the overlap of this mode with the wall, because the wall is actually the gain region. And so the overlap between the gain region and our eigenmode basically defines the imaginary part of the complex eigenenergy. So by exploiting this really nice property, we can emulate non-Hermitian two-level Hamiltonians with these systems, and ultimately engineer exceptional points. So exceptional points are spectral degeneracies that arise in non-Hermitian systems. They were originally proposed in the context of quantum non-Hermitian physics, but then, of course, because it is hard to observe in the quantum system, the classical optical and microwave communities run away with the concept, in particular in context of PT symmetry. There is a certain array of really interesting counterintuitive properties of the system that occurs near the exceptional point, but the two smoking guns, if you wish, of exceptional point are the following. It's a branch point singularity, so it possesses a topological, so it has a topological Berry phase, meaning that if we go around an exceptional point in a space of two control parameters of the system, if we go around the circle once, we will never return to the initial state. It branches off to a different branch. If we go around twice, we come back to the initial state, but with accumulated topological phase. And the second property of the eigenstate, of the exceptional point, is related to the one surviving eigenstate. So both eigenvalues and eigenstates coalesce, and the surviving eigenstate is chiral. It has a well-defined chirality because the two eigenstates coalesce with a phase plus or minus pi on 2. So our plan for modeling this, for observing the exceptional point in exciton polariton condensate, is to create a fragmented polariton condensate, which is an optically trapped condensate that has occupation of two or more modes, and use two control parameters of the system to bring these two eigenstates to degeneracy, and then test this non-trivial topology of eigenvalues around the exceptional point. In order to do this, we have constructed quite an elaborate system, which is an exciton polariton cyanide billiard. It's a quantum billiard. a reflective potential in which the exciton polaritons sit. And it is created by an optical pump shaped by a DMD mirror, composed of a rectangular area and a scattering corner. Once again, in this system, we can image in real space eigenmodes and eigenvalues. This is a spectrum, and of course, eigenvalues are complex, so we have the position of our resonances, energy, and finite line widths. Okay, so the reason we went into the trouble of creating this cyanide billiard is that Hermitian cyanide billiard exhibits quantum chaos. And as Michael Berry showed back in 1981, that means that there is an abundance of avoided crossings at very low energies already in this billiard. And these avoided crossings near degeneracies actually are very sensitive to the change of shape of the billiard. We deal with non-Hermitian cyanide billiards, so it has both avoided crossings and crossings. This is a theoretical calculation. This is experimental calculation. You can see that they match pretty well, but what we really want is focus just on one pair of two levels near the degeneracy. So we can write an effective Hamiltonian for this, for interaction of these two levels. And we'll see that the eigenvalues of this Hamiltonian are complex and essentially are controlled by the sum and difference of the eigenvalues away from the near degeneracy point. So if we really want to test the non-trivial topology of the exceptional point and go around the closed contour around the exceptional point, we need to find two parameters in the system that control the movement along the two axes, delta E and delta gamma. It turns out that in our system, these two parameters are the radius of the scatterer, which changes the inner area of our billiard, and so changes the position of energy levels, and the width of our walls, which doesn't change the inner area, so doesn't affect the distance between the energy levels, but it does change the overlap between the modes and the gain region, and therefore affects the effective gain parameter. So these two parameters, experimental parameters, allow us to move along two axes in this space and therefore complete the traverse around the exceptional point. And so when we do this, start from the red state here on the red branch, go around the exceptional point once. So we start from the dipole mode, go around the exceptional point once, we come to something completely different. It's a different branch and it's a weird sort of tripole mode. And then we complete the same loop in the same direction a second time, come back to our dipole, but now look at the phase. It is flipped by exactly pi. So we have accumulated our Berry phase by going around the exceptional point twice. Yes?
So generally, Berry phases are discussed in adiabatic systems, right? But you have dissipation, so it's a non-adiabatic traversing.
Yeah, so this is not evolution in time. This is evolution in the parameter space.
Yeah, even Berry phase is like a parameter space evolution when you consider equilibrium systems.
Yes, so you're referring to the adiabatic evolution in time, though, whereas I'm referring to the traversing the points of a bunch of trajectories in the parameter space, each of which corresponds to a steady state.
But there is a dissipative factor that decays or rises exponentially in your stationary phase, right? So there is a dissipative part also there in the phase, stationary phase, which will decay or exponentially grow.
Look, maybe we should discuss it later, but yeah, the notion of adiabaticity really doesn't enter here. because in terms of a time evolution, when you go to a non-Hermitian system, it is at least theoretically impossible to adiabatically encircle an exceptional point because it always induces non-adiabatic transitions between the steady states.
Is it theory or experiment?
This is experiment. This is experiment, and we were quite excited about this experiment. First of all, because it was published in Nature, and secondly, because and secondly, because this is the first time that the exceptional point was actually detected in the quantum system, in the microscopic quantum system. Because we actually took this whole non-Hermitian physics back to where it started from, into the realm of quantum physics. Okay, so this is the exceptional point. What about the chirality of a mode? It is quite impossible to tell, really, in this system because the modes are a bit too complex. But very recently, and this paper is now in the archive, we have constructed something more simple in which the exceptional point, the degeneracy occurs between two dipoles. So this is kind of asymmetric ring resonator. This gives you an idea of what the pump looks like, and this is just the schematic of the two modes sitting in this resonator. The eigen modes of this resonator are not Laguerre-Gaussian modes, they're Inky-Gaussian modes, so these are two lowest order modes. And so away from the exceptional point, these two modes are proper dipoles, which is confirmed by the interferometric measurements. But as we, once again, find two parameters, which happens to be the widths of one half of this resonator and the detuning between the exciton and photon, so effective mass of polariton, if you wish, we observe a very nice chiral mode with a deterministic orbital angular momentum, which is a vortex. So by now we have observed both sort of characteristics of the exceptional point. Now, I'm risking to run over time, but what I really want to also talk about, at least briefly, is the fact that everything I talked about so far concerns condensates which are in fact somehow pushed away from these repulsive walls created by the reservoirs. So condensate and reservoir are spatially separated. What we want to understand is what happens if they overlap strongly, because the reservoir provides a source of particles and, of course, a strong source of fluctuations. So what we tried to probe is the properties of the condensate, which is strongly coupled to this reservoir. And for this, we really tried to understand the fine details of condensate formation in a single shot regime without averaging over many, many realizations of the experiment. So what we did is we excited our Bose-Einstein condensate by using a pulsed regime, an intense 140 femtosecond pulse, which is then isolated from all subsequent pulses. So an experimental technique called pulse picker picks at least no more than 100 such pulses in a second, which results in a single pulse arriving during a lifetime of a condensate and reservoir. So the photoluminescence from the condensate rises, and then we let it decay completely. So if we average over about 10 to the 6 of such realization of condensations, we see at the first glance nothing out of the ordinary. We see a nice smooth condensate forming somewhere above this soft threshold. And in the momentum space, we see something slightly weird. We see that the polaritons don't thermalize as they approach the condensation transition, meaning that they don't occupy the slow polariton curve uniformly. But then above the condensation transition, they go into ground momentum and energy states, as they should. So in principle, we expect nothing out of the ordinary here until we actually look at images of the single-shot polariton condensation. And this is what we see. So this end is highly photonic light polaritons. These are excitonic heavy polaritons. And we see that in both regimes, they exhibit strong shot-to-shot fluctuations, and also the photonic polaritons exhibit this really strong spatial filamentation with filaments extending up to 0.1 millimeter. Right? So what is going on? Once again, surprisingly, this behavior is very well described by I would say glorified mean field model, which is the stochastic classical field model. This can be derived quite rigorously from truncated Wigner approach. So essentially what it has is two essential ingredients, is stochastic fluctuations that are taken into account and relaxation of the chemical potential. Again, this is a phenomenological way to describe the energy relaxation in the system. If we were doing it properly, we would go to a microscopic approach, which takes into account interaction with phonons through proper Lindblad Hamiltonian. But this is just a quick and dirty phenomenological way. So you can see that the agreement between the experiment and theory is quite remarkable, at least as far as the single-shot real space imaging concerns. We see this highly filamented condensate in a photonic regime and something that smoothes out significantly with growing excitonic fraction. So I'll give you a summary of what we've learned from this analysis, and then I'll show you how it works. So it turns out that shot-to-shot fluctuations are an inherent feature of spontaneous condensation. And the reason for this strong filaments is that photon-like polaritons have very large kinetic energy, so they simply fly away from the excitation region. Exciton-like polaritons, on the contrary, are heavy, do not travel far. There is no thermal occupation of a low polariton branch, but nevertheless, two processes, which is energy relaxation due to non-radiative processes, interaction with phonons, and density depletion of the reservoir drives the condensation into a ground momentum and energy state. And this energy relaxation is far more efficient for exciton-like polaritons, which makes sense because they're more heavy, so they engage with phonons. Okay, I will skip through this because I'm actually running severely out of time. But what I want to emphasize is that the condensate that forms in a highly photonic regime is actually a very statistically non-trivial state. It is a state that has long-range order, which we confirm by interference. You can see that the interference fringes extend all the way down to the length of the filament, but it has absolutely no second-order coherence. The G2 of this state goes almost all the way to 2, which is indicating a state with really large statistical density fluctuations. And this is actually in line with what was recently observed for a condensate of photons. And when we change the detuning and make our polaritons more excitonic, they suddenly behave like a proper condensate should. They have a long-range order and also very nice G2 that goes down to 1. Coherent field. So this is also now on archive. All right, so to summarize, where we hope to go with this research is to explore several possibilities. First of all, there is a dispute or debate about whether these fluctuations, shot-to-shot fluctuations, actually a result of modulational or dynamical instability of the condensate. We hope to prove once and for all that this is not the case. Secondly, with regard to coherence, there is again a discussion in the community, long-standing discussion, that probably this long-range order is actually quasi-long-range order and is due to the Berezinski-Kosterlitz-Thales phase rather than BEC phase. So with a single shot imaging, we are actually hoping to see or not see formation of paired phase defects, vortices. And finally, there's quite a bit of theory on how Kibble-Zurich scaling laws can be modified for an open dissipative system, and this is a prime sort of system to test these things in. Thank you very much.